Hi, today we are going to talk about solving exponential equations. So let's get started. When we're talking about exponential equations, that means we are looking at equations that have variables in the exponent. So if you notice here, this 3 to the x, my variables in the exponent. We're trying to figure out 3 to raise to what power is going to equal 20. Here we also have that variable in the exponent. So we're going to look at a couple different methods to solve these exponential equations. First thing we're looking at is something called the base-exponent property. And this says if two expressions have the same base and they are equal to each other, then notice that these exponents, x and y, must also be equal to each other. So let's look at that. If we have 2 to the third, that must equal 2 to the third. Like those exponents have to be the same. If we have x to the fifth equals, let's say, x to the a, then a here has to also be 5. As long as the bases are the same and these are equal, then those exponents must also be equal. And that's going to really help us when we are solving these exponential equations. So I'm going to move on to our first example. So we want to solve 2 to the 3x minus 7 equals 32. And so again, using that base exponent property, that means that if we can get these bases to be the same, then we can solve for that exponent. So we need to think about, can I change this side of the equation into something that has a base of 2? And this is where it's good to be familiar with your like different exponents and powers. So, 2 to the first power is equal to 2, 2 to the second power is equal to 4, 2 to the third power, that's 2 times 2 times 2, which is 8, 2 to the fourth power is 16, 2 to the fifth power is 32. And that's what we are looking for. Again, we're trying to say, can we change this side of the equation, the right-hand side, so it has the same base as the left-hand side? And knowing what we know about these powers of 2, we can say that this 32 is equivalent to 2 to the fifth. And once we're able to write that, now we have that base exponent property. Here we have the same base on both sides. They're equal to each other. Therefore, it means this exponent must be equal to this exponent. And so we can solve this by saying 3x minus 7 must equal 5. And then we'll solve that equation. Our first step to solve that is to add 7 to both sides. And so that's going to give me 3x equals 12. And finally, to solve for x, we divide both sides by 3. And we find out that x equals 4. That's our solution. And of course, we can always check that answer. It's a good idea to check your answers, whether you're doing it mentally or writing it all out. But if I plug in x equals 4, we get 2 to the 12 minus 7, which is 2 to the fifth. And we do know that that equals 32. So that works. So again, using the base exponent property to get the same base and solve for that exponent. So now let's look at the second example. Again, if we're using the base exponent property, we want the base on the left to match the base on the right. So we need to think about powers of 3 that are going to give us 1 over 27. Well, as soon as we see that we have this fraction, that means we're going to have a negative exponent. Because if I have like 3 to the negative 1 power, that's 1/3. If I have 3 to the negative 2 power, that's 1/9. It turns this base into a fraction with that reciprocal. 3 to the third power is 27. So if we're looking at 1 over 27, that means it's going to be 3 to the negative third power. And so that's how I'm going to rewrite this right-hand side. I'm keeping the left-hand side the same. And on the right-hand side, 1 over 27, that's the same as 3 to the negative third power. And again, the reason now that we do this is so we can use that base exponent property, which says if the base here on the left is the same as the base on the right and they're equal to each other, then that means their exponents are equal. So now I can say x squared plus 4x equals -3. And I need to now solve this for x. Now we can see that this is a quadratic equation. So my first step here is going to be to set it equal to 0 and see if I can solve it by factoring. So I get x squared plus 4x plus 3 equals 0. If I'm going to try to solve this by factoring, I'm looking for two numbers that multiply to give me 3, that add to give me 4. So that'll be positive 3 and positive 1, because again, when I distribute, that'll give me 1x plus 3x, which is 4x in the middle, and then that 3 times 1, which is 3. And then if we use the zero product property to set each of those factors equal to 0, we end up with x plus 3 equals 0, which means one possible solution is x equals negative 3, or x plus 1 equals 0, which means one possible solution is x equals negative 1. Now, we definitely want to check these answers because it's not always the case that an exponential equation is going to have two solutions. So the fact that we got two solutions here means, let's make sure that maybe one of them, maybe both of them, I don't know. So let me come over here and check this. So I'm going to start with the negative 3. So if I plug that into the left-hand side, I'm putting parentheses here. That's going to give me 9 minus 12, which is 3 to the negative 3, which is 1 over 27. So it looks like x equals negative 3 is a valid solution. Cool. Let's also try negative 1. So when I plug that into the exponent, again, I'm looking at my original equation, plus 4 times negative 1. So when I do that negative 1 squared, that's positive 1 minus 4. This gives me 3 to the negative 3, which is also 1 over 27. So it does look like we have two solutions here for this equation. So we can have x equal negative 3 or x equals negative 1, and they're both solutions to this problem. Okay, so let's try one more example. Now you'll notice here that we have 3 different bases. So we have 27 equals 3 to the 5x times 9 to the x squared power. And so again, if we're using that base exponent property, we want to make the bases the same. So hopefully, again, if you're familiar with powers of 3, we see that these are all powers of 3 that we have here. We can take 27 and rewrite that as 3 to the 3rd power. We can take this 3 to the 5x and leave it for now. This 9, we can rewrite that as 3 squared, but it's still being raised to the x squared power. And now we want to kind of combine this right-hand side. So let me see if I can simplify this a little bit more. Here, when I have 3 squared raised to the x squared power, I can multiply those exponents. This is an exponent rule that if we have a power raised to a power, we can simplify it by multiplying those exponents together. So I can multiply this 2 times x squared to just write this as 3 to the 2x squared power. I can also combine this right-hand side as well. Because remember, for the base exponent property, we just need 3 to a power on one side and 3 to a power on the other side. So since we have these two terms with base 3, we can combine these by using another exponent property. It says if we are multiplying powers that have the same base, we can combine them by adding their exponents. So since we are multiplying these two powers that both have base 3, we can combine them by adding the exponents, 5x plus 2x squared. And now we have our equation set up properly to do that base exponent property. So here we have base 3 on both sides. They're equal to each other. That means their exponents must be equal. This exponent of 3 must equal 5x plus 2x squared. And now we need to solve that. And so this is another quadratic equation. So I'm going to, I think, move over here to the left and solve that over here. So I'm going to start by subtracting 3 because I want to make this equal to 0. And I'm going to move over and solve that up here on the left. So now I'm going to write this right-hand side in standard form. I'm going to have 2x squared plus 5x minus 3 equals 0. And we want to solve that by factoring, hopefully, if it factors, or we want to use the quadratic formula. There's a lot of different methods that you can use to solve quadratic equations. I have a whole other video about that, so you can look for that one. But for right now, I'm going to factor this. Since there's a 2x in front, I'm going to do this. And then let's see, we need 3 times 1. So here, this factors into 2x minus 1 times x plus 3, because if I distribute, I get 6x minus 1x, which is 5, and then I get negative 1 times 3, which is negative 3. And once I have my factors, I can set each factor equal to 0 and solve for x. When I add 1 here and divide by 2, I get x equals 1/2. On the other side, I subtract 3, we get x equals negative 3. And so just like I did on the previous example, I want to check my answers and see if they are both solutions or if just one of them is a solution. So going back to my original problem, I'll plug in x equals 1/2. So over here, we get 3 to the 5/2 times 9 to the 1/4. Okay, that's a lot. So I'm just going to type that into my calculator. If I do 3 raised to the 5/2 times 9 raised to the 1/4 power, it gives me 27. So that means that this does work. X equals 1/2 is a valid solution. I'll also now check that with my second answer, x equals negative 3. So again, in my original problem, everywhere there's an x, I'm plugging in negative 3. So that means I have 3 to the negative 15 power times 9 to the 9th power. Again, I'll use my calculator. 3 to the negative 15th power times 9 to the 9th power does equal 27. So both of those were valid solutions. So our solutions are x equals 1/2 and x equals negative 3. All right, so now we are going to look at how we can solve exponential equations by using a different method. And this method that we're going to be talking about is the property of logarithmic equality. So you'll notice that this says if we have two logarithms that are equal to each other and they have the same base, then it means that these values here must also be equal to each other. Notice how similar it is to that base exponent property. Having the same base means that the exponents are equal. Similarly with these logarithms, having the same base means that these values are equal. And this double arrow means that it goes in both directions. And that's what we're going to be using to solve these equations. That means that if we have two things that are equal to each other, they might not look the same, but if they are equal to each other, we can apply a logarithm with the same base to both sides and use that to solve our equations. So you're really going to need to be familiar with properties of logarithms. So let's start with this example, 3 to the x equals 20. I want to kind of talk about why the base exponent property doesn't work here. So as we saw with the base exponent property, we need our expression to have the same base on both sides in order for us to be able to solve for that exponent. Now, in this case, it's not possible for us to change this 20 into something that has a base of 3. Because as we've seen, 3 squared is 9, 3 to the third is 27. There is no exact power that's going to give us a value of 20. So using that base exponent property isn't going to work here. This is where we're going to use this property of logarithmic equality. So instead, what I can do is I can apply a logarithm to both sides of the equation. And you have a choice here as to what base you want to use. We can apply log base 10, log base 15, log base 2, whatever we want to both sides. I'm just going to use the common logarithm. So I'm just going to use log and apply that to both sides. And what that means is that we now have log 3 to the x equals log of 20. And by doing this, we can apply the properties of logarithms to move this exponent. So now that we have the log of something raised to a power, we can use the product rule to take that exponent and move it to the front of our logarithm. So this becomes x times log 3 equals log 20. And now we can algebraically solve this for x. Since x is being multiplied by log of 3, we can divide log of 3 on both sides. And now we type this into our calculators. So in my calculator, I look for that logarithm button. I'm doing log of 20, dividing it by log of 3. And that's going to give me a decimal of 2.726833.028 and so on. And you would round that according to whatever your instructions say. And now we can check that answer, like I like to do, by going back to the original format of the problem, 3 to the x equals 20. And now if I take 3 and I raise it to this power, that should give me my answer of 20. Now you have to realize that since we're rounding, it might not exactly equal 20, but as long as I'm close, so if I take 3 and raise it to that power, I see that I get close enough to 20, so we know our answer is right. Again, as soon as we start rounding decimals, then we're losing accuracy in our solution. So if you put a rounded answer here, it's not going to equal exactly 20, but it should round to 20. So that's how you know you're right. So this property of logarithmic equality is going to be really helpful for us now as we are solving these exponential equations if we can't get the bases to be the same. So let's look at another example. So here I have e to the 0.08t equals 2500. So we're trying to figure out what power here will give us this value. Again, it's not an easy thing to change 2500 to have base e. So I'm going to go ahead and use that property of logarithmic equality. So I'm going to apply a logarithm to both sides. Now, since we're using a base of e, a wise choice here would be to use the natural logarithm. So if we have a logarithm of base e, that's the same as the natural logarithm. And the reason that's going to help us is because if we take the natural logarithm of something with e, that's just going to cancel out and make our calculations a lot easier. So that's what I'm going to do. Again, with that property of logarithmic equality, you can use whichever base you want when you're solving these. But in order to make this as efficient and simple as possible, I'm going to do that natural log. And I have to remember that I'm applying that natural logarithm to both sides. And again, as I said, now this natural log of e, those cancel each other out, and we're left with 0.08t equals the natural log of 2500. And again, algebraically now, we can solve for t by dividing both sides by 0.08. Since t is being multiplied by that value, we can divide it in order to solve for t. And again, this is where you have to do some calculations in your calculator. I'm going to do the natural log of 2500. I'm using this TI-84. Make sure you close the parentheses, divide that by 0.08. And hopefully, if you're following along, you should get 97.80057,514. And we assume that that's an irrational number that just continues. And again, as we said in the previous problem, you can check your answer by taking this value and plugging it in for t in the original problem. And so let's do another one, right? More examples. So again, here we can see that it's not going to be possible to get the bases the same. So let's apply that logarithm to both sides. In this case, I'll just do the common logarithm. So I'll do log of 4 to the x plus 3 equals log of 3 to the negative x. And again, by doing that now, we can take those expressions that were in the exponent and multiply them by the logarithm. So these exponent values get moved to the front, And so now it's important here that I have parentheses because the entire log of 4 is being multiplied by x plus 3. On the other side, negative x is being multiplied by log of 3. And so we have a couple different options here. When we're trying to solve an equation, we want to get all of our x terms on one side. So in order to help me do that, I'm going to go ahead and distribute this log 4 on the left. Remember, log 4 is just a number, so we can treat it as just a coefficient. So when I multiply log 4 times x, I'm going to write that as x times log 4. And then here's 3 times log 4 equals, I'll just drop those parentheses, negative x times log 3. And again, as I was saying, when we're solving for x, if we have two x's, one on each side, we want to get those on the same side of the equation so that we can eventually get an answer in the form x equals. So we have a couple options here. I don't really love negatives, so I'm going to add x log 3 over to the other side. And I'm going to do two steps at once. I'm also going to take this constant and subtract it on both sides. So I'm moving my constant terms to the right, and I'm moving my variable terms to the left. So what I have now on the left is x log 4 plus x log 3. On the right-hand side, we have negative 3 log 4. We're almost there. So again, we're trying to solve for x. What do we do about the fact that here we have two terms that have an x in them? Well, what we can do is we can factor that common x out. I can divide that out from each of those, which means I am left with log 4 plus log 3. So this is the reverse of the distributive property. Again, what I did there is I factored out the x from each of those. And by doing that, now I can say, okay, since x is being multiplied by this entire expression, I can divide that entire expression on both sides to solve for x. So my solution is actually this entire expression. X equals negative 3 times log 4 divided by log 4 plus log 3. I know, it's a lot. And then we can type that into our calculator if we want to get an approximate answer. This is the exact answer. For the approximate answer, when you're typing this in your calculator, just be careful. I'm doing negative 3 log 4 divided by, and then I want to put this entire expression in parentheses, just so my calculator knows that that's the entire denominator of the fraction. So I'm doing parentheses, log 4 plus log 3, close that parentheses, and then I have parentheses within parentheses. I can kind of show you what that looks like. And then when I press enter, we get our rounded solution. And so this is approximately equal to negative 1.67365 8, if I kind of round it. So we have the exact solution written as this fraction, or we have the approximate rounded solution. And again, you can check your answer, take 4 to the power of that number plus 3, and see if that is the same as 3 raised to the negative of that power. I don't have a lot of space to write it on there, but checking your answers is always a great way just to kind of make sure, that you did the problem right. Now, I believe that is everything for solving exponential equations. So hopefully you found this lesson helpful. I plan to add more videos to my YouTube channel as I get used to this whole thing. So thank you very much for watching. If you have any questions about any of these, then feel free to comment and I will do my best to address those questions. All right. Thank you so much. Take care. Bye.